Let me welcome you all to Jnanavardhini, FDBPI's weekly knowledge sharing session. Today, our speaker, Mr. V. N. Premanand, is going to talk about the possibilities of quantum computing and its use in AI. Quantum computing holds immense potential for transformative advancements in AI by increasing its speed, efficiency, and accuracy, outperforming conventional computers. Mr. Premanand is passionate about the subject and has been regularly engaging engineering students on this. He's a director of Pragya AI, a startup engaged in research and development of next-gen technology solutions, and currently vice president of Cyber Society of India. He has 30 years of experience in the information technology space, engineering management, training, consultancy, and research, and 10 years in telemedicine and cybersecurity. He has worked on many government and NGO projects, implementing technology platforms in the health sector and facilitating telemedicine for rural areas. He's a regular speaker at professional forums and TV shows and guest faculty at various engineering college and management colleges. Very happy to have you today. Over to you, Mr. Preman.
Thank you. Thank you for the kind introduction. Good evening, ladies and gentlemen. Good evening, members of FDPPI, members of Cyber Society of India, and other friends. Good evening. Let me start today's topic. I would like to introduce you with a simple concept of how a quantum computer work, and then probably what are the applications and how it is helping artificial intelligence. I will share my screen now. Okay, hope it's visible. Quantum computing.
Yes.
The concepts and the AI possibilities. So what is quantum computing? This is an emerging technology, and it relates to the laws of computing mechanics at the quantum level to solve problems that are too complex for today's computers, which are even large enough as the supercomputers. So today, IBM Quantum makes real quantum hardware. So quantum computers, the concept has been evolving over a period of last 2 decades. And then scientists have been tinkering with many tools and finding ways to make it possible. So here at IBM, they have done a lot of research, and the quantum computing has now become real. So these machines are very different from classical computers in the sense they are more powerful, multiple times powerful. So what is exactly quantum computing? It is the area study focused on developing computer technology based on principles of the quantum theory. So quantum physics, quantum mechanics, as we call it. So it gives enormous possibility for the computers to operate in different states and perform tasks simultaneously using all kinds of permutation and combination simultaneously, which is not possible with today's classical computing. So why do we need this? So we have classical CPUs, multiple cores, multiple GPUs, but even then, having something like a map-reduced technology with multiple Linux clusters running and using transformational technology to manifest one tool to do computations over all these multiple computers at the same time, even that finds really impossible for some complex problems. So complex problems are the ones which cannot be done in linear ways. So modeling the behavior of individual atoms in a molecule is a problem. Another example is sorting out ideal routes. If you have 100 tankers in a global shipping network, this is also complex. So such complex problems are not solvable by today's classical computers. So how do quantum computers work? let us see, these are machines which are smaller than the large supercomputers today. These are smaller, but they have their own problems of maintenance. So a classical quantum computer needs to be kept at a very low, um, you know, uh, temperature, which is even like 1 Kelvin, which is minus 273 degrees centigrade. So then we have some complex, definitions like superfluids and superconductors. Let us see what are they. So we have our desktop computers today, which uses a fan to cool. Quantum processors need to be very cold, about 100th of a degree. That's what I said, minus 273. Super cool, super fluid. So in such situations, the molecules, atoms, and electrons behave in a different way, which makes us possible to make them compute in a different fashion than today's existing computers. So at those ultra low temperatures, certain materials behave in a certain way, which are very feasible for large scale computing. So like electrons, they can move without resistance. This makes them something called superconductors. So when electrons pass through superconductors, they match up, forming certain pairs, which are called Cooper pairs. These pairs can carry a large charge across barriers or insulators through a process known as quantum tunneling. Then we have a concept called Josephson junction. So two superconductors placed on either side of an insulator is called a Josephson junction. So how do you control? IBM's quantum computers use Josephson junction as superconducting qubits. Now I will come to the definition of qubits. What are they? We know about bits. We'll see what is qubits. So now we see the concept of firing microwave photons at these qubits. Then what happens is their behavior changes to hold, change, read out individual units of quantum information. So the information that can be stored in quantum computers is much larger than the classical computers. Then we have a concept called superposition. I will come to this qubit later. Let us see what is superposition and entanglement. A qubit itself isn't very useful. So qubit is something like a bit, but it is different from that. Placing the quantum information it holds into a state of superposition, which represents combination of all possible states. So groups of qubits in superposition can create complex multi-dimensional computational spaces. So this helps in solving complex problems. This may be a little abstract, but let us see a few more slides, then it will become more clear to you. Then there is something called entanglement. Entanglement is a quantum mechanical effect that correlates the behavior of two separate things. So when there are two qubits are entangled, changes to one qubit impact the other directly, even though they are in a very large distance also. So quantum algorithm leverage these relationships to find solutions to very, very complex problems that are not possible with supercomputers. So how do we make quantum computers useful? So we have computing hardware and software. Then the IBM kind of companies also have a roadmap to take it further. So quantum advantage will not be achieved with hardware alone. So you have to have a lot of software. The software today, many software development kits like Qiskit from IBM is available. Then we have something called Circ. These are all open source. Python. Python is the language, programming language that is used extensively. Python is also used for information in artificial intelligence, machine language, and deep learning. Achieving quantum advantage will require new methods of suppressing errors. So when we maintain the hardware at low temperatures, there are also possibility of getting errors. So increasing speed and orchestrating quantum and classical resources will also lead to management of errors properly. Then let's see what Google is doing. So Google says they are 47 years ahead. So after going on a silent revolution for a while, they have announced that they have a significant advancement in their quantum machines. So according to a research paper from Google, the company's latest technology surpasses the capabilities of current classical supercomputers. So Google's paper shows the ability of larger quantum computers to handle noise, which refers to the interference that poses a threat to delicate states. So the quantum bits are stored in delicate states. So how they are handled, the research says we can definitely assert the demonstration and falls of the quantum computational beyond classical capabilities. So that is some academic information for you. Google also says a quantum company based in Cambridge views this development as a significant milestone. So they published a paper named Phase Transition in Random Circuit Sampling. So even as early as 2019, machine that consisted of 53 qubits, the fundamental units of quantum computers, the latest generation now operates on 70 qubits. So I have to give you a definition of qubits now. Let us see the slide and move further. So Google's exponential growth in quantum computers is going to be felt in the near future. Google faced opposition from competitors also like IBM and Microsoft that the disparity between their machine and traditional supercomputing was a little bit exaggerated, but they're still trying to prove their worth. What is Microsoft doing? Microsoft is also having an Azure platform, and they have something called Q hash as a computing language. So IBM quantum computing is far superior to the ones I mentioned now. So the iconic IBM Quantum System 1, this was created at the multiple emerging technologies, and System 1 is the first integrated platform for commercial use. So this supports 27-bit Falcon, 65-bit qubit Hummingbird, and 127-bit qubit Eagle processor. So the next stage, as they say, is IBM Quantum System 2, which is built to support next level of evolution of the quantum computing. So it will integrate the classical compute resources and other cooling systems necessary to serve large process and future architectures. Now we come to the real definition of quantum computing. So computer that can do regular computers can't do. That is what quantum does. These computers are called quantum computers. They are different from the existing ones. They use something called qubits instead of bits. So what is a bit? It is a single unit where you store information. A bit is like a light switch that can only be either on or off, that is 0 or 1. But what is a qubit? It can be both 0 and 1 at the same time, and also a combination of 0 and 1 and many combinations. This means quantum computers can do many things at once and at much faster pace. It is like having many workers on a task together instead of just one. So here, the quantum computers, these are having gates which are similar to the AND or NOT XOR, which is with the normal computers that manipulate data and produce output. These gates are made using transistors. As you know, that was prevalent since 1940s, and now evolved to become the integrated circuits. But quantum computers use a different methodology. How? So they have a unit called qubit to process information. A qubit is similar to a bit, but it has properties such as superposition and entanglement, which means the qubit can exist in both 1 and 0 at the same time. Seems a little bit difficult to understand, but this allows quantum computers to perform certain calculations much faster than traditional computers. So in a real quantum computer, qubits can be represented by various physical systems. So here we have the AND and NOR gates and on the integrated circuits, whereas in a quantum computing scenario, you will have various physical systems which are electrons with spin, photons, polarization, trapped ions, and semiconducting circuits. All this combined gives the ability to perform methodology which is far superior to supercomputing today. With the ability to perform multiple complex operations faster, quantum computers will revolutionize many industries, including healthcare. So qubits can do something really cool. Let us see how they do it. They can be in two states at the same time. It's like having two helpers working on a same task. It's like a coin. Either you have heads or tail or both, but a qubit can be both 0 and 1 at the same time. This means that quantum computers can do many things at once. That is, today's computers are doing things on a linear fashion, whereas the quantum computers can do multiple tasks such as these parallelly. This ability of superposition makes it more powerful. So let's go a little deeper. The qubit can represent multiple values at the same time, rather than just a single value like a classical bit, like 0 or 1. It can show multiple values. How? A qubit is similar to a bit, but it has quantum properties. So 0 and 1 states. In a real quantum computer, qubits can be represented by various physical systems. We saw that. I'm repeating that. So regular, sorry. So qubit can exist in an infinite number of superpositions of 0 and 1, each corresponding to a different probability distribution. So something like a Monte Carlo method. So this allows a qubit to perform multiple calculations simultaneously. So the ability of qubits exist in multiple states at once enables the execution of quantum algorithms. So we have different algorithms. One example, in regular computers, a group of 4 bits can represent 16 different values in a linear fashion. However, in a quantum computer, group of 4 qubits can represent all 16 combinations and simultaneously, and the tasks on the 16 can be performed parallelly. A simple example of superposition is a Grover's algorithm. People who have worked on Grover algorithms would be able to appreciate this. The search algorithm, it is a search algorithm that is now used in quantum computing. What it does is search an unordered database with number of entries, n entries in root of n steps. Whereas a classical algorithm would take n steps exactly, that is linear fashion. So there is one more thing called Shor's algorithm, which is a quantum algorithm that can do factorization, a composite number in polynomial time. That is progressive polynomials. So that is considered hard for classical computers. They would crash. So this algorithm has important applications in the field of cryptography, as many encryption methods rely on difficulty of factoring large numbers. So let's see quantum entanglement. So where, say for example, you have 2 toys, a car and a boat. So let us put the car in one room and boat in another room. We are not looking at both. So you will know what's happening on the other toy by just looking at this one. So if there is some operations which is performed on this boat, it will also happen on the other toy, which is the car. So this is really important for quantum computers, because this method to perform calculations much faster than regular computers and communicate in a better way. So 2 or more quantum systems become correlated in such a way that one system cannot be described independently of the other. So whatever happens here happens the other also. So entanglement is used for performing large scale, multiple complex calculations on a single computer. So there are other algorithms such as Bell states, which has a maximal entanglement states of 2 qubits. Grover's algorithm also uses this. So now we come to advantages of the quantum computing. Quantum computers can perform calculations faster and suited for very large complex mathematical calculations. They also have the ability of parallelism. Like I said, the 16 operations which can be done linearly in a normal computer can be done simultaneously. So cryptography, when it comes to methods and algorithms which are used today, which takes a lot of time, can take lesser time using quantum computers. So which would mean it will become more resistant to hackers quickly. If you take chemistry, quantum computing can simulate behavior of molecules because they are at a very low temperature. That is not possible in the classical computing. This could lead to new discovery in drug design, material science, and other areas. So it is good for pharma companies. What are the disadvantages? Quantum systems are extremely sensitive to environment. So you have to keep them in very cold states and for performing certain computations. Errors may occur. When it occurs, you have to redo the process. Scalability, another major challenge. Building a large-scale quantum computer with a large number of qubits is extremely difficult. Currently, research is going on. The number of qubits that can be controlled and manipulated in a laboratory setting is still small. So which limits the commercial potential of quantum computing. Error correction, of course, is a major challenge. Errors are corrected using error correcting codes, but in quantum computing, the errors are much more difficult to detect and correct due to the nature of quantum system. So you don't know at what state every moment it may be in a different state. So there is also a lack of algorithms. High costs in building and maintaining quantum computer is extremely expensive. Large scale quantum computer is quite high. Companies like Google and IBM can build, but not all others. Power consumption, also this makes it difficult to scale up quantum computing to larger systems because it becomes prohibitively high to maintain power. So this is a simple comparison between classical and quantum computers. You see classical and quantum computers on the right hand side. The basic unit, its bits are 1, whereas here it's qubits 0, 1 or both. Superposition not possible. Qubits can exist in multiple superpositions like 0, 1, 0, 1, combination of 0 and 1. Entanglement is not possible. Qubits can become entangled. So you have multiple simultaneous calculations. Processing performs tasks one by one. Linear can perform multiple calculations simultaneously. Speed limited by Moore's law and physical limitations. Whereas here, faster, more efficient for certain problems. So you have to choose quantum computing for specific purpose. You have to see the application and then choose various industries and fields. So cryptography is one example. Optimization and chemistry are 2 other examples. So which companies are building this? IBM, Google. So what has IBM done? The company has made significant progress in this field. So it has the IBM Quantum 1 and Quantum 2, which is a 20 qubit machine. Google has been working on this and they claim that they have a 72 qubit bristle cone quantum computer. So the company claims that this quantum computer has reached quantum supremacy. It is yet to be accepted. There are other companies like Alibaba, which has invested heavily and it has 11 qubits quantum computer. Rigetti Computing is a startup company that is building and developing superconducting qubits based quantum computers. They offer a cloud-based platform. Intel is also having one, which is a 49-bit. And there are other companies like D-Wave. You can look at D-Wave. I have a slide about D-Wave. I'll show you, which is bringing the first commercially available quantum computer. They claim to have built the first commercially available one, but their system is not fully general purpose, mainly used for optimization. Xanadu is another Canadian company which uses photonic quantum computing and is based on the manipulation of light particles to perform large-scale compositions. It uses superconducting qubits. They are still working on a general purpose quantum computer. So these are the tools. One is called the Qiskit from IBM, CARQ from Google, and QAsh from Microsoft. So applications: optimization, logistics and transportation, smart factories, biomedical, engineering design, energy systems. On the other hand, if you see big data analytics for finance, insurance companies, healthcare, transportation, and construction. Machine learning, automotive, clinical research, pharmaceuticals, and finance industry. So now the AI comes into picture when we say machine learning. So AI is a superset. Machine learning is a subset of AI, as you know, and deep learning is a subset of machine learning. So deep learning, machine learning combined, models being built, and AI can be used for generating various models for pharmaceutical and finance industry. Monte Carlo simulation, as I told, multiple probability calculations that is useful for oil and gas, finance, manufacturing, bioinformatics, and law. For this, quantum computing can be used to achieve faster methods. Material science in biomedical, architecture, automotive, and and pharmaceuticals. So now I'm going to tell you in a layman's language how quantum computers work. Now let us suppose we have a travel agency. We need to move a group of people from one location A to another location B. To keep this simple, let's say that we need to move 3 people. So they are named Alice, Becky, and Chris. And there are 2 vehicles that have been booked for this purpose. And we want to figure out who gets into which taxi, which vehicle. So one more information is that who's friends with who and who's doesn't like who. So the problem is like this: Alice and Becky are friends, Alice and Chris are enemies. Becky and Chris are enemies. These are information given to us. The problem, the goal is to divide this group of people, of 3 people, into 2 taxis to achieve the following objectives. What are the objectives? Maximize the number of friend pairs and minimize the number of enemy pairs in the same car. So let's first think about how we can solve this using a regular computer, and then we go about solving with a quantum computer. Okay, let us see how we do it with a regular computer. That is a classical today's computer. So we'll need first to figure out how to store the information with bits, not qubits, bits. So we will label the 2 vehicles as taxi number 1 and taxi number 0. Then you can represent who gets into which car with 3 bits. So as an example, can we set 3 bits to 0, 0, and 1? This will represent Alice gets into taxi 0, Becky gets into taxi 0, Chris gets into taxi 1. So let us have all possible configurations. Since there are 2 choices for each person, what do we have? We have 2 into 2 into 2, which is 8. So there are 8 ways to divide this group of people into 2 cars. So let us see the possible configurations. ABC 000, 001, 010, 011, 100, 101, 110, and 111. So using 3 bits, you can represent any one of these combinations, 8 combinations. Now using a regular computer, how can we determine which configuration is best suited? To do this, we have to compute the score for each of them. And the score will tell us the extent to which the solution will achieve the objectives. What are the objectives? That is maximizing the number of friend pairs and minimizing the number of enemy pairs. That is in the same vehicle. So score, let's see the definition of our score. The score of a given configuration is defined as friend pairs sharing the same car minus enemy pairs sharing the same cars. So for example, we have Alice, Becky, and Chris all get into taxi 1. With 3 bits, this can be expressed as 111. So in this case, we are observing that one friend pair is sharing the car. Alice and Becky is a friend pair. On the other hand, 2 enemy pairs are sharing the same car. That is Alice and Chris and Becky and Chris, according to our earlier definition. So how do we calculate the total score? Which will be as 1 minus 2, which will become minus 1. So with all this setup, we can solve the problem. With a regular computer, to find the best configuration, we will need to go through all combinations and see which one achieves the highest score. So let us see the table. We have 001, which is minus 1. 001 is the best solution. So 000 is minus 1. So 00 and 1 is one of the best solutions. There may be another. So 010 gives us minus 1. 011 also gives minus 1. 100 also gives minus 1. 101 also is minus 1. Then we have something called 110, which again becomes a positive 1, which is another best solution. So there are 2 best solutions. As you can see, the 001 and 110 are both achieving the score of 1. So this problem is very simple for a classical today's computer. When will it become too difficult? Now we have 3 people. Okay, so we have 8 combinations, 8 possible configurations. Suppose, imagine if you have 4 people, in which case you will have 2 to the power of 4, which will become 16 configurations. So when this becomes multiple, that is when we say n people, we will need to go through 2 to the power of n configuration to find the best solution. So making 16 linear computation is okay, but making n linear computation will become very, very difficult. So if there are 100 people, what happens? 2 to the power of 100, which is 10 to the power of 30, which is 1 million, million configurations. So this becomes extremely difficult to solve for today's supercomputing infrastructure with multiple clusters and MapReduce techniques. So we go to the other side and see how we can solve the same problem with this quantum computer. So again, let's imagine, let's get back to the case of dividing 3 people into 2 taxis. So there are, we know for basic, we have 8 different configuration, 8 different possible solutions or configurations or combinations, as we call it, 000, 001, and so on. With a regular computer using 3 bits, we were able to represent only one of the solutions at a time. That is linear. However, with a quantum computer using 3 qubits, we can represent all 8 solutions at the same time. There are debates ranging from whatever to see what it exactly means. So let us first examine first qubit of 3 qubits. When you set it at both 0 and 1, it is sort of creating 2 parallel worlds. So this may sound a little bit bizarre. So if you have heard about parallel worlds, then you will be able to appreciate it. This has some, relation to our Vedic texts also there, where they talk about parallel universe and parallel worlds. So the qubit is set to 0. In the other one, it is set to 1. So now what if you set a second qubit to 0 and 1, 2? Then it is not sort of creating 4 parallel worlds. So 4 parallel, processes. So in the first world, 2 qubits are set to 0, 0. In the second one, they are 0, 1. The third one, they are 1, 0. In the fourth one, they are 1, 1. So similarly, if you set 3 qubits to both 0 and 1, you will be creating 8 parallel worlds. Okay, so with these same combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. It is a little bit strange, but let us think in this manner. When you apply some sort of computation on these 3 qubits, we will actually be applying the same computation in all those 8 parallel worlds at the same time. So instead of going through each of those potential solutions sequentially one by one, we can compute all scores at the same time. It is like forking. So in this example, your quantum computer would be able to find one of the best solutions in a few milliseconds compared to our earlier classical computer. In reality, to solve this problem, we need to give your quantum computer 2 things. All solutions represented with qubits, function that turns each potential solution into a score. In this case, this is the function that counts the number of friend pairs, enemy pairs on the same car. So having these 2 things in your quantum computer will spit out one of the best solutions in a few milliseconds. Now, in theory, a quantum computer is able to find one of the best solutions every time it runs. However, in reality, when there are errors, we need to find the best solution. It may have to run another time. So these are the same solutions we saw, and the errors become more prominent as problem becomes more and more complex. So in practice, you will have to run the same operation on a quantum computer dozens of times to achieve maximum possible outputs. Then we'll pick up the best result out of many results. But since it does it in a very short time, it is okay. So how it scales? When there are 3 people, we need to divide into 2 cars. The number of operations we need to perform on a quantum computer is 1. With a classical computer, when there are 4 people, the operation increases. But whereas here it is still 1. When there are 100 people also, the number of operations is still 1. So with a single operation, quantum computer computes the score of all 2 to the power of 100, whereas it takes millions of computation process on a regular computer. So it is probably best to run your quantum computer dozens of times, or maybe hundreds of times, to pick out the best results. However, it's still much better than running the same on a regular computer, which will be hundreds or thousands of times slower than this. So as I told you, D-Wave is a company for those who are interested in tinkering with this technology. You can look at this cloud dwavesys.com leap You can use this free tool to solve thousands of problems. You can sign up and navigate and see what they offer. This is a cloud-based platform which you can tinker. Now let's see what AI and quantum, how they're related. Quantum computers are designed to perform tasks. We know they perform accurately, efficiently, and quickly than conventional computers. There are specific applications that quantum computers achieve greater heights compared to their counterparts. Quantum computing and AI are similar in terms of transformational technologies. AI needs quantum computing because AI needs large sets of data. Although AI produces functional applications with classical computers, it is limited by the capabilities of the existing computers today. Quantum computing will provide larger applications, larger perspectives of multiple computations on large set of data. So there are also difficulties with quantum computers, as we have seen. The slightest disturbance in a quantum system, say a photon emission or a wave radiation, can cause quantum computation to collapse. So it is called decoherence. So quantum computers are very, very sensitive and must be totally isolated from all external interference during the computational phase. Error correction is another problem. So what is the nature of quantum computing? Is we saw that there may be errors due to different reasons, and we need to run it again and again multiple times. So error correction is very critical. Even a single error in a calculation can cause the validity of entire computation to collapse. So the keeping it cool, keeping it in a different place, keeping it very secure is important. How we observe the output closely related to the above two, retrieving output data. Probably checking one small process with a classical computer and maybe relating that with a quantum computer will give you a sample of output observance. And then as it scales up and as it scales up, you have to maintain the cooling system, other critical factors, and then see the output. So applications of quantum computing and AI, as we see today, it can be in processing large sets of data. So machine learning, deep learning, probably having large sets of data in a government database where they track criminals, kind of solve complex problems faster, better business insights for commercial computing, integration of multiple sets of data. So when it comes to deep learning, integration of multiple sets of data, which gives its ability to act on its own, put some machine learning on top of it, and achieve absolute AI for manifesting today's applications with a much powerful, data processing capabilities. So advantages of computational superiority and achieve results that are not possible to achieve classical computers. It can also be used in healthcare where we have predictive analysis of diseases, which is very helpful when we use deep learning, machine learning. And when these large sets of data are to be processed and compared with existing data sets, it becomes more useful putting it on a quantum platform. So what do? We are producing 2.5 exabytes of data every day. That's equivalent to 250,000 libraries of Congress or content of a million laptops. Every minute, every day, 3.2 billion global internet users continue to feed data banks. So you have tweets, Pinterest, Facebook likes, and other things. So quantum computers are designed to manage these kinds of data, along with uncovering patterns, spotting anomalies very, very quickly, and do error corrections. Also optimize the same for solving all kinds of business problems, for making effective decisions. So solving complex problems faster, which would take today's computers many years to calculate. So what Google claims is something which takes 47 years to calculate, we can do it with quantum computing in much lesser time. So developers can do multiple calculations with multiple inputs simultaneously. That is what parallel computing, parallel processing, simultaneous processing of data using multiple states of qubits. So by this, people will gain data supremacy. And what it would not normally take 10,000 years to perform for a classical computer can be done in 200 or 300 seconds. The key is to translate real world problems that companies are facing today into a quantum language. That is where the difficulty is. So it will take a few more years for this to become real and really commercial. So better insights and models. So we have various industries like pharmaceutical, finance, life science, and which are losing their ties with classical computing rope because of lack of power. So to have a better data framework and better models, quantum computers play a huge role. So if, for example, creating better models with quantum technology will lead to better treatment of diseases. Like health sector, for example, COVID-19 research cycle from test, tracing, treating of the virus can decrease the financial burden. And in the banking sector, it can prove very efficient. And in logistics chain also, it will become very useful, which is again connected to manufacturing industry. So integration of multiple sets of data is a key. So multiple number of sets from multiple sources. So here again, the deep learning comes into place. Quantum computers use the best methods of the deep learning combined with the machine learning. The ability to handle so many of exabytes of data will become really useful. That will also solve business problems in various fields. What is the future holding for quantum computing? The market is $2.2 billion, and the number of installed quantum computers will reach around 180 in 2026, with about 45 machines produced each year. So machines are not in common place, but they will be in places like Google, D-Wave, IBM, Microsoft, and kind of places. And maybe there will be a lot of startups also like D-Wave coming into picture. So cloud access to these will be possible. People can use this platform directly, the hardware, use the tools such as the ones like QAsh, and 75% of this quantum computing revenues will be with the larger companies. And more widely, today potential and end users are inclined to do quantum computing over cloud. So these larger companies where they have larger, hardware infrastructure and software tools will prove to be useful in the long run. So many people are since using the cloud today. So on a parallel track, quantum software applications, developer tools will become available. Number of quantum engineers and experts will grow as the infrastructure grows in the next 5 years. So this will make it possible for more organizations to harvest the power of transformation technologies. So AI, ML, DL will become really possible in business scenarios by using quantum computing. Of course, universities can look at adding quantum computing into their syllabus. One last thought. The Vedic influence. So we have these leading scientists of 20th century. Let's see what they say. After discussions about Indian philosophy, some of the ideas of quantum physics that had seemed so crazy suddenly made much more sense. That's what Heisenberg said, who coined the uncertainty principle. The unity and continuity of the Vedanta are reflected in the unity and continuity of the wave mechanics. So Erwin Schrödinger, again, another Nobel laureate, he studied Max Muller's translation of Sanskrit texts in German, and then he has used it in various research papers. So when I read Bhagavad Gita and reflect how God created this universe, everything else seems so superfluous. Albert Einstein. Whenever I give a lecture on quantum physics, I feel as if I'm talking on Vedanta. Peter Dar. Schrödinger himself said that this discovery has some blood transfusion from east to west, because he was hinting at the existence of matter in both particle and wave form. So that is already available in our ancient philosophy. So with that, I would like to end this presentation. Thank you for listening. I would like to take the questions now.
Yeah, friends, any questions? I have been a student of physics. Okay. And when I passed out of my MSc, quantum physics was one of the topics which we were studying. Of course, from 1973 to now, quantum physics also has perhaps made progress. And it has come to the context in which I am now working, which is in computers and other things, which is very interesting. Okay. I don't know whether Prem is also from physics. Are you from physics, Prem?
Mathematics and electronics and computer science combined.
Okay.
I'm a student of physics, and I'm ardently doing some research on one thing, sir, the consciousness and how it relates. Our Srimad Bhagavatam has some parallels with quantum physics.
Yeah. So it's good that you brought in that linkage, because Heisenberg's principle of uncertainty itself is something which is very interesting in terms of quantum possibilities. Okay. Of course, understanding quantum computing is not easy. I'm sure many of the people who attended must have felt the complexity of this. You have actually tried to explain it with some examples on how it can be used. And also you have given an example of a particular website and said free tools are available. I suppose some people will start checking out that.
Yes, sir. IBM has a tool. Then this Microsoft and Google, they have all put up some open source tools.
Yeah.
D-Wave is really interesting. They are a startup from Canada. and they are very close to bringing a general possible quantum computer.
Good. Questions, please.
Yeah, this is Sarath Babu,
Yes, sir.
former executive director of SETS. So very interesting talk. I just would like to know, probably you haven't touched the quantum entanglement. I think the
Yes.
what idea you have given is the quantum superposition aspect of it.
Yeah.
So yeah, would you like to enlighten us on quantum entanglement? That is one.
Okay.
While you have given, as I appreciate the views of Albert Einstein and all foreigners, why not we project our own scientists with such views like Sir C.V. Raman or mathematician Dr. Ramanujan? Probably that if you add, it will have a lot of value. Why we
Definitely.
should only feel that foreigners are only appreciating? Why Indians won't appreciate?
No, no, no. It is taken.
I'm just,
sir, because
because I only, that's the first thought I got. So I just thought I will share it.
Indians
No,
may
no,
not
no.
be appreciating that is the problem.
No, not that, not for that. See,
Yeah. It's in a
Indian,
lighter vein. In a lighter vein. Don't take
no,
it
no, no.
seriously. I'm just
I
telling.
will let me
Yeah.
explain that. Let me explain that. So Indians have have understood the concept of duality and unity in their own DNA, and most of them just like that in their lives they have known this. But whereas the Westerners, they have tried very hard to learn Sanskrit and read our texts and then try to find out the parallels. So that is why I mentioned that.
It's fine. It's fine. Just
I will
maybe,
definitely
yeah.
include it in next time when I do this talk.
It's okay. Thank you.
Thanks for indicating that. I have to do it. It is my duty to show that what Indians, how they have done it.
Sure. Great.
Yeah, Ramesh.
Yeah, Mr. Prem, I think this is really a good session, maybe understanding the fundamentals onwards and how it moves. Quick question is, how does the startups taking up this quantum computing? And we know some of them are coming up with this, knowing that the power required for them to handle these calculations is high. How are these startups building the quantum computing or their startups? Any idea?
See, I will tell you with my own experience. So if you have to do a large scale computing, even see, for example, deep learning, machine learning. So AI, I teach AI at a few universities. So when student asks, we give them, we tell them that, probably go to AWS or some platform where there is some, tools available for us to tinker. Some credits are available free. So what they do is they go to the cloud. So since it requires a larger, say for example, for a simple, search technique like a Google on a smaller scale, we need a cluster of 10, 15 Linux machines connected and orchestrated together with something like a MapReduce technology. So that may not be available in their campus. So they go to the cloud infrastructure where some companies like IBM or somebody is offering. Similar to that, today, when a few couple of years back, if you look at supercomputers, only our Center for Development of Advanced Computing, CDAC, Pune, they had developed the supercomputer. So people would go and see what is that, and large, powerful computing machine. So it is not available to the common man. Whereas today's cloud technologies allows you to go and learn. So for example, if you want to become a quantum computing engineer, maybe you can look at these tools, maybe go to D-Wave website, see their cloud infrastructure, subscribe, get register, get into that, and try their platform and see what tools. There are also examples of some simple problems to start with. For example, if you want to do a quantum computing example, so what I have to do, I have to define a problem, then see how I can define a circuit and then make the qubits, whether using photons or electrons or other, physical resources that are available, or a combination of many. Probably start with photons and then do a simple example and then go further. So that is where today's startups on this kind of supercomputing or quantum computing, as you call it, they go to these cloud infrastructures which are offered by larger companies, start doing things, and then maybe I'm not sure how they will make their own product. It may be not feasible immediately, but maybe over a period of 3 or 4 years, people will come out with some open source tools, or there are people who start doing this and come out with tools that helps this by using Python. People who are experts in Python maybe developing tools for um, uh, complementing quantum computing on a larger scale.
Yeah, actually, that's what I want to clarify. I think you answered it right. And by the way, Dr. Sarat Chandra Babu, who spoke now, he was also ex-CDAC director.
Yeah,
and he's a,
I have met him once in Hyderabad. I don't know whether he remembers. That's long back, 15 years back.
Yeah, your name when it comes, I think I know. But only thing is I was not able to connect with the face and the thing. But yeah, it's very interesting, points that you have brought in, and especially comparing the classical and with a good example. It was very interesting.
I think this was, I knew that it was a little bit abstract, but I hope you would have found that, the taxi example, which clearly defines what quantum computing is.
Yeah, that's
Yep.
true. That's
And come to the entanglement, sir. When there is an entanglement, you have the two different things which are correlated. So one, what we do here on this object happens on the same in the other world. So which means multiple sets like this can perform that 16 calculations at the same time. So that is how entanglement works.
No, in Prem, and also Sharath, if you can, in entanglement, we say that if one particle is, say, having a spin in one direction, the entangled particle will have a spin in the opposite direction. This kind of working in different these things, opposite directions, is it the inherent nature of this entanglement?
To some extent, yes.
So if I make this bit is presently 0, then the other one will be 1. Now, if I change the 0 to 1, the other one will become 1 to 0.
Yes.
So this reverse action is something which needs some explanation of why it should be reverse.
For when it is 0 and 0, then it becomes easy for us to perform parallel calculations.
But it
When
doesn't happen like that, no? If one is
it doesn't happen.
entangled particles, if one is 0, the other one will
The
not
other one
be
is 1. So when we have multiple calculations at the same time with two different possibilities, then it is useful.
So you can actually mirror that and build that mirroring into the calculation.
Yeah.
But I'm wondering why nature has created this reverse this thing in entanglement. I understand China has actually experimented entanglement across large distances, about a mile or so. In India, have you come across any research on this quantum physics?
I am not sure, sir.
Sir, Professor Chandrasekhar from IISc and IMSc, he is pursuing this area, and he is using such technologies in the quantum key distribution area. So the research is going on, and it was supported by, I think, DST and other organizations.
Okay. Our own Indian Institute of Science is not working on this. Any idea?
Sir, Professor Chandrasekhar is actually now in IMSc on deputation to IISc, something like on lean or something. So he is representing both. That's the
because it requires large resources also to build a quantum computing lab.
Yeah, they make prototypes. Yeah.
Sir, in that case, CDAC should have been attempting that, no?
Yeah, I would know. They have to build a center for
Yeah.
this kind of temperature maintained.
That is the most difficult thing. Maintaining at 1 Kelvin.
That only large universities or government can do. Nobody else can do that. Others can make use of that back-end quantum computing resources, and then perhaps run classical computing outside the network. Is it not? That is how it has to be handled, I suppose.
Yeah, I think, sir, there is IASC professor, I am immediately not getting the name, and CDAC together providing the quantum simulator using the HPC system. That is supercomputer. That is more or less ready because IASC professor has already developed the simulator. Only they have to make it available to all. That is once again METI funded project to CDAC and IASC. That's I think more or less ready, sir. It's they are opening up for the public to.
Where, in Bangalore? In Bangalore?
Yeah, it will be in, I think supercomputer could be in Pune or Bangalore, but the work is being done by the professor of Indian Institute of Science, which is already done. And along with him, IIT Roorkee is also involved. There's a kind of 2-3 organizations together. I understand it's totally ready. CDAC Bangalore also is involved in that.
Okay. Now, IBM and other people, of course, they have developed bits, but from which resources are they working? In US, I think there must be some resource from university resource which must be made available to them.
I am not very sure, sir, but IBM is also providing, that is, you can register and get the the services, and you can work on quantum computing on a simulator. They will give you number of qubits on the real quantum computer also. That one has to register, and as an institute or an individual, I am not very sure, but IBM is quite promoting that.
They also have a learning program wherein they are giving a certificate-based quantum computing for developers.
Yeah.
Yeah.
Of course, our community of people who are the audience here, they are more concerned about whether quantum computing can be used to break, say, encryption. That is one of the concerns of all the security people.
Yes.
But, one is resources required will be very large. So that is one deterrence. And at the same time, if quantum computing can be used for breaking the encryption, it can also be used for creating complex encryption, I suppose. So the race will be like that. If we start using quantum computing for creating security, then we can reasonably dent the challenge of criminals using quantum computing for breaking the encryption. What do you say? Your reactions?
If it is from me,
one of my ex-colleagues, is one of my ex-colleagues of his software, they have founded this company called QNU Computing, QNU Computer, QUNU. They have prepared this quantum key distribution kit, and they're funded by, I think, Cisco also, and a couple of other things, and they sold some stuff to the defense. His office is based out of Bangalore only on MG Road. I've met him once, but not very much in touch with him on this topic of quantum safe cryptography, right? I'll share the website address in the chat. So on this, not been in touch with him for some time now, but maybe if you
they have mentioned proactively securing data for post-quantum era.
I've shared the website at QNU Labs.
I think what is right now commercially available is also the quantum key distribution. You are all aware that Diffie-Hellman algorithm is there for key distribution. But through quantum mechanics, if you do, it's a fail-proof operation. And if even somebody tries to intervene, it will be collapsing, right? Because it is a quantum nature. Whereas when it comes to encryption and decryption, there is once the source algorithm and all is implemented in a sizable computer with quantum supremacy, there is going to be breaking of the that is factorization problem will be solved. Once the factorization problem is solved in no time, the RSA algorithm on which entire key distribution is not key distribution, keys are dependent is going to fail. So that's where people are worried. And so there are two aspects they are looking at. Quantum encryption is one aspect, and classical computers itself, they are trying to use the post-quantum cryptography, which is quantum resistance algorithms using new mathematical problems using lattices, etc. They are trying to, NIST has put a challenge, and they have shortlisted a few algorithms, started with a large number of algorithms. Now they are recommending only 3 + 3, 6 algorithms in the recent finalized list. So those things people are working now to implement. So it's that way, two angles. One is use the quantum mechanics and strengthen. The other is use the classical mathematics, which are not yet being solved by the quantum computers, which quantum computer itself may struggle to solve such mathematical problems. That is the post-quantum cryptography. So both angles, scientists and people are working, and post-quantum cryptography is more or less practical. People started implementing even in the practical systems. Quantum key distribution is basically using the quantum principle and distributing the key over the photonics, the single source of photon or dual source of photon and so forth.
I think they are using this also in one of the, I saw somewhere an Israeli company using these photon techniques for firewall, which is based on, unidirectional method.
Correct.
Okay. Okay, thank you.
And Raman Research Center is also working in Bangalore. Madam Orosai Sinha is quite done a lot of work in quantum communications. So one probably her talks are also available on the net, also on the website also.
Yeah, Manju.
Sure. So thank you all, sir, for organizing such nice thing, and I hope we keep doing these talks regularly.
Thank you, sir.
Thank you.
Thank you, sir. Thank you for your inputs.
Thank you, Mr. Prem, for explaining the fundamentals of such a complex subject in simple terms and with illustrations. Making it easier for us to read and learn further about the applications and new developments. Thank you very much for joining us today and delivering an interesting and informative session. Thank you, Dr. Sharad Chandra Babu, and for joining the discussion. And thank you, Nav.